Welcome to Horizons Tech Talks, where we stay up to date on the developments in quantum computing from across the research community. We provide the stage and benefit from the exchange of ideas with those who are pushing the technology and the industry further. Our third guest, who is here with us today, is Dr. Yingkai Ouyang, who is a research fellow at NUS. Yingkai was previously at the University of Sheffield, where the work on the topic of the talk was done. His other interests include quantum error correction and quantum metrology. We're very excited to have him here today to present his results. The audience should write in your questions in the chat box on Zoom, and we'll get to them at the end. The floor is all yours, Yingkai.
Thank you for the invitation and the very nice introduction. Today, I'm very pleased to share with you some work I did at the University of Sheffield on a topic in quantum simulation. And this talk is about compilation by stochastic Hamiltonian sparsification. It's quite a mouthful, but in a nutshell, what I'm going to show you today is a proposal of a simple algorithm that we have for quantum simulation. And this work was done with David White and Earl Campbell. So what is quantum simulation? In quantum simulation, you want to understand what happens when, for example, a molecule with a certain Hamiltonian evolves with respect to time. So you can discretize the Hamiltonian to represent this Hamiltonian in a qubit space. So for example, a molecule with n orbitals, you can represent it as a Hamiltonian with a large number of terms, L terms, where the number of terms is like scales polynomially with the number of orbitals. And over here, each pj can be interpreted to be a Pauli operator, for instance. And so the idea is that in order to understand what happens to the molecule with n orbitals, all you need to do is to simulate this effective qubit Hamiltonian over here. The coefficients over here, Hj, would describe, are important in describing what the molecule actually is. So one way of doing the quantum simulation is instead of using this entire Hamiltonian at once, to decompose the simulation into elementary gates. So instead of simulating H in one go, this Hamiltonian H in one go, we are going to simulate each of these Pauli gates one at a time. So we do a Pauli rotation, we do a rotation with respect to Pj, and then for J from 1 to L. And by doing so, we can simulate e to the iht, e to the minus iht, up to some approximation error. And because there is some approximation error, we would like this approximation error to be as small as possible. And at the same time, we want the number of gates that we use, these elementary gates, to be as small as possible. But there's a trade-off between the two. As the number of gates increases, the simulation error decreases. But if you want the simulation error to drop to a very low level, you probably need a large number of gates. So the question is, given a fixed number of gates, what is the minimum simulation error we can have for this quantum simulation problem? So there are many different approaches to quantum simulation, and the work that I'm going to talk about today will hybridize two prior approaches to this quantum simulation problem. And this the standard approach to quantum simulation is this technique known as trotterization, which I'm sure many of you are familiar with. But for those of you who are not familiar with it, I'll introduce it in no time. So, but from the performance perspective, you can see I show over here the performance of two prior quantum simulation techniques. So for instance, there's some work by Charles Ostrander and Su, which is represented by this orange line over here. As you can see, the x-axis is corresponds to the number of gates, the number of elementary gates that we're going to use, and the y-axis is the error bound. as you increase the number of gates, the errors can get smaller at a certain rate. And there is this recent paper, well, there's this paper by Campbell, which uses a different approach to quantum simulation. And because it uses an approach different from this orange line, it has a different slope over here. For different number of gates, one of the bounds, one of the techniques outperforms the other. And the question is, can we have a scheme that inherits the goodness of both approaches to outperform both previous algorithms simultaneously? And well, we're going to show that it is possible. So, so now in this slide, I will introduce to you what is known as trotterization. So in order to simulate this Hamiltonian, this unitary evolution, e to the minus I h t, where h is the sum of many terms, what one can do is to use this product over here. So you have a product of e to the minus I s h of j, where each h of j is basically each of these individual terms over here. So by chopping up this overall Hamiltonian into many small pieces, given that s is a parameter that is sufficiently small, you can be guaranteed that this unitary over here is going to be a good approximation of this overall unitary, where the approximation error is order s squared. So if s goes to 0, you can see that this error will vanish at a quadratic rate. Of course, in quantum simulation, you're not, you may want to simulate for a time that is longer than an infinitesimal, than a tiny time, little s. So, so if your time is large, maybe you may worry that the error would be scaling to be quite large, but no worries. You can basically chop up the overall time into little time steps over here. And for each little time step here, you apply this trotterization, and the overall error will still be of order s squared, no matter how large this t is, given that you chop up this t in a certain number of way, in this way. So there are r pieces over here, and r is given, will correspond to the number of effective gates that we are going to use. So the error will scale overall as g times order s squared. All right. So in order to perform the analysis, to proceed to the rest of the talk, I need to introduce something rather technical. So, so instead of, because I'm talking about a unitary over here, but it's quite cumbersome to work with unitaries. So we can go to this so-called semi-group picture. The important thing about the semi-group picture is that it allows us to write down the evolution of a quantum state in a very compact form. So for instance, we know that a state rho will evolve according to the Hamiltonian hj in this following way. Basically, you multiply the left side and the right side by these corresponding unitary matrices. But it's very annoying to write everything on the left and the right every time. So why don't we just have a notation where you just apply something on the left? And this thing over here is known, can be called the Lindblad operator over here. You can call it the Lindblad operator. And basically, this operator acts in this way. So by writing it in this way, you can express this unitary evolution in this Louvre representation. So if you want to do this trotterization over here, if you don't have this trotterization, the overall Hamiltonian is given by the sum of all these h's. So the overall Louvre representation will be given by this simple form, e to the SL over here. So this is the notation that we are going to use. So with this notation, we're going to get a bit more technical about what trotterization is again. So in trotterization, we're going to multiply these unitaries, these Louvre evolutions piece by piece. But as you can see, when I introduced this trotterization procedure, I have not been very explicit about the order in which you're going to multiply these trotterization terms. In fact, you can do it in either the forwards direction or the backwards direction. Like you apply like L1 first and L2 first, or you apply like LL first and L minus 1 first. You can, in fact, you can do it in your favorite permutation of these index labels. But for the moment, I'll just restrict myself to the forwards and the backwards direction. But no matter which order you do this trotterization, the error, the overall simulation error will be the same. It will be of order the number of repeats of over here times little s squared, which will overall have this scaling factor of t squared L over G. Recall that L corresponds to the number of terms in this Hamiltonian. G is the number of gates that you are willing to, the total number of gates that you're willing to do. And T is the simulation time. So in a very interesting result by Charles Ostrander and Su 2 years back, they showed that if you do the forward trotterization and the backward trotterization with equal probability, then you can have the simulation error to scale as order SQ instead of order S squared. This is really amazing because such a simple modification immediately cuts down the simulation error by an order of magnitude. And this is really awesome, in my opinion. And there is another very nice work by Campbell, also 2 years back, where he showed that you can have a different type of scaling of the simulation error. Instead of having the simulation error scale with this capital L, which is the number of terms in the Hamiltonian, you could have it scale with respect to something different, like the sum, for example, the sum of all these Hamiltonian coefficients over here. And this type of performance would be very advantageous in the scenario where capital L is very large, but lambda is small. And this is, in fact, the scenario for many realistic quantum chemistry simulations where the distribution of the H coefficients is not uniform, but rather follows some kind of power law. So there's a lot of Hamiltonian coefficients that have vanishing contribution, so but with a huge number of terms. And just to give you an idea of how many these terms can be for like a simulation of like even very small molecules like methane, you could have L to be like 100,000 terms. So this problem could really benefit from this this approach, which was called the Q drift approach, which Campbell named. And so in the Campbell approach, he basically chooses each Hamiltonian term to appear with a certain probability instead of doing trotterization. So he just picks the Hamiltonian terms with probabilities that is proportional to this the Hamiltonian coefficients magnitude over here. All right, and in this talk, I'm going to talk about how we could combine the virtues of these two different approaches. So look, this random trotter approach is really, since it's random, we can call it a stochastic approach. So let's say we can take the first three letters of stochastic, which is STO, right? And this Q-drift approach is really, you're doing some sparsification approach because you're not going to use all of the L terms in the Hamiltonian very much. You're only going to use a tiny fraction of them with high probability. So this is a sparsification approach. And by combining these two approaches, we have this approach, which we call the sparsto approach, which is the natural combination of sparsification and stochastic approach, sparsto. All right, so what's this sparsto approach? So in this sparsto approach, just as before, we are going to use this sparsification approach where we're going to pick terms in a Hamiltonian to appear with certain probabilities. But we also want to take into account the fact that we can have the trotterization to go forwards and the trotterization to go backwards. So on top of picking these trotterization terms to appear with certain probabilities, we are furthermore going to have them occur in some forwards and backwards directions. And what we're going to do is we're going to bound the simulation error, and we're going to use the diamond norm for those of you who care about the diamond norm. Yes. So what's the main? So I'm going to state the main result informally. So the requirements of the main result is that we have this Hamiltonian that we want to simulate, and it has this decomposition where these HJs are basically coefficients, and PJ is really arbitrary. PJs is arbitrary such that it has an operator norm of 1. And you choose each of these Hamiltonian terms with probability PJ. And you set the number. So for every trotter step, you're not going to pick just a single Hamiltonian term, as in Campbell's Q-drift approach. Instead, we're going to pick like a random number of terms, and the average number of terms is going to be mu, which corresponds to the probability of us picking each term. Then the simulation error is going to scale in this way. It's going to have something that scales like 1 over g, and something that scales like 1 over g squared, essentially, and with some higher order terms where this this norm of this, where this u vector can be basically calculated based on the p vector, the probability vector, and the Hamiltonian coefficient vector. And in the limit where we pick all of the Hamiltonian terms, which corresponds to the standard trotterization, which it will collapse to basically the Charles Ostrander-Su forwards and backwards trotterization approach, we reproduce their simulation error, which has this type of 1 over g squared type of behavior, and the error scales as the total number of terms in the Hamiltonian over here. All right, to be even more explicit in what the simulation error is, I can tell you what this u vector is. This u vector depends on the h's and the p's in this very interesting way. And this k is really a bunch of it's just a constant which depends on 2 more vectors over here, and also depends on lambda. All right, so this is the result, and because we have this very very explicit result over here, we can make the substitution of p equals to 1, like for all of the p1s to pls, and you can see that obviously the u vector, v vector, and w vector go to 0, and everything becomes really simple. I mean, this term goes away, and we're left really with just this term, and that's exactly what we have. And the algorithm is really simple to write. I mean, I've already told you in words what the algorithm is, but the point of me showing this slide is that, well, the algorithm fits on the slide, which is really nice. All right, so now how do we get the upper bound on the simulation error? It's really easy. So we just use the favorite technique that, I mean, the most immediate idea that you would have in mind if you were to try to obtain the bound. We'll do a Taylor series expansion of both the ideal quantum channel, the ideal process over here, and also the algorithm over here. So you can try to do a Taylor series over here. So let's do these Taylor series, and after we would see how the leading order terms cancel out in this difference over here, and then we have to bound the tails, and we can bound the tails by using some clever techniques that arise from calculus, really. All right, so in order to obtain bounds on the simulation error, we first present some interesting combinatorial identities. Also consider some vectors. You have some vectors and you want to, some real vectors and you want to sum them in some way. For example, you want to sum them such that their indices like AJ and BK, the J and the K are always distinct indices. You want to have this type of sum, but you want to express this sum in terms of, you want to have this sum exactly in a very simple way. And so we are able to derive these identities by hard work. All right, so these sums will come into play when we obtain our upper bounds. So essentially, we are going to do some Taylor series. And when we do the Taylor series and check the leading order term, I'll just show you the leading order term and tell you the answer. Oh, the difference between the leading order term is just 1 minus 1 over pj times this lj squared. That's nice. So that means I can take the diamond norm of this overall thing, and I can find it is easily upper bounded by this. So I immediately get this leading order term over here. This leading order term is the most important. So if I want to, so now let's go back to a higher level, and we have to understand what are we actually optimizing over here. So the H vectors over here is what's given to us in the problem. We can't change the Hamiltonian coefficients. But what we can choose are the probability vectors over here. So the question now is, what choice of probability vectors is going to be the optimal choice to minimize the simulation error? Now, we can pose this as a convex optimization problem. So, of course, I've derived an upper bound for the simulation error that looks fairly complicated. But if we take just the leading order term, it's really just something that depends as it's really depends on this term over here, just a h squared divided by pj, and you want to minimize this. And this is a convex function because 1 over p is a convex function. And your constraint over here is that as a linear constraint, you want the sum of the probabilities to be equals to some expected number of gates that are applied per trotterization step. And there's another linear constraint, which is a very natural constraint. Your probability vectors are at most 1, which must be true for your probability vectors. And of course, your probability vectors are non-negative, which is also a linear constraint. So, so what's going to happen for your probability vectors is that you can divide the probability vectors into 2 cases. For one scenario, the pj will be equals to 1. Without loss of generality, your pj is either equals to 1 or is less than 1. When pj is 1, we say that the index j is in the so-called active set. That means that the constraint over here is active. That means as pj equals to 1, that means this inequality here is tight. But there are some j's for which the inequality is not tight. And this this active and inactive set will be important when we are trying to optimize this problem. In fact, we are going to now consider this linear ansatz. Consider pj to be proportional to the Hamiltonian coefficients for some constant c. Of course, your Hamiltonian coefficients could be very large. So you don't want this to apply all the time. So basically, if the Hamiltonian coefficient is too big, you set pj to be equals to 1. So basically, you have the probabilities to be looking something like this. So this is what I call the linear ansatz. And what we show is that this linear ansatz, this choice of probability vectors here, is actually the optimal one. And we derive the optimal C for which that minimizes this objective function over here. And in order to prove that this linear answers is the optimal probability vector over here, we appeal to the optimality condition for any nonlinear continuous optimization program. So for that, we write down the Lagrangian of the problem, which is really the objective function plus the Lagrange multipliers multiplied by the constraints. So it's one constraint over here, this first constraint, and then you have the second type of Lagrange multipliers multiplying by the constraint that the probabilities is no more than 1. And then we can check then we impose the optimality conditions of any nonlinear optimization program. Because this optimization program is convex, the necessary conditions for optimality is also sufficient, and so we know exactly when our probability vector is going to be the optimal one. So for that, let us just check the stationarity condition with respect to the Lagrangian over here. Just take the derivative; it's really easy. And then you can find when this is equals to 0, for which you find that Pj is equals to this simple thing over here. And then you use the so-called complementary slackness conditions for and from there you can solve for the optimal Lagrange multiplier U over here. Because okay, from the optimality conditions in convex programming, you will find that whenever Pj is less than 1, Pj square root U times Pj must be equals to this. So this means that if you want to find what Pj is, all you need to do is to find U. All right. But then feasibility condition tells you what U is depending on the other parameters over here. So by inverting this equation over here, you can solve for square root U and therefore find the optimum Pj. All right. So now, so we use this linear ansatz with the optimal value of C to minimize the simulation error, and we check the performance of simulating simple molecules such as ethane over here. So over here, ethane requires like 100,000 terms, which is quite large in this Hamiltonian. You can see Q drift is over here. Basically the random forward and backwards trotterization is over here. And for every point you can see on this graph, this hybrid approach, the sparser approach, is strictly better than both of the combined approaches. Over here, the red line shows the second order approach of doing this forward and backwards random trotterization. So you can do higher order approaches to this thing over here, but in this parameter regime over here, this Charles Ostrander-Su's second order approach is not even close to sparser. So let us check out the performance of our algorithm with respect to different molecules such as carbon dioxide and propane. Propane has like a huge number of terms, but in all of these approaches, we can see that sparser is doing really well. So this brings me to the end of this of my overview of what we have done for this quantum simulation problem. So in a nutshell, we have revisited the problem of trotterization, and we have an upper bound on the simulation error when we have an algorithm that uses sparsification and stochastic trotterization, and it improves on the previous best known bounds. And we believe that this sparsification technique can be later incorporated into other like post-trotter methods, although we have not really explored them. And with that, I like to end the talk and invite questions. Yes.
Yes, thanks, Yingkai. That was really impressive. Like with these algorithms, like you say, it's only on one page, but the devil's in the details. So really, really nice. I'm going to quickly pop open the chat and see if there are. Okay, so there are no open questions in the chat box, but Joe has some questions. So Joe, would you like to ask them yourself? Yeah, he's coming.
Sure, yeah, that would be great. Actually, I have a ton of questions that stem from this. But one of the questions I have is basically about, it's about the metric you're using for error. So you mentioned that you're using the diamond norm.
Yes.
So this is something we've been thinking about quite a lot internally as to what's the best way to measure practical error. So kind of measure what error is effectively on average, like what's the expected error rather than what's the worst possible case. And I guess you can imagine that these would diverge quite substantially in the case of some channels.
Yes.
And if you imagine doing a calculation for this, given that most states are close to maximally entangled, it amounts to really working out just what's the 2 norm between Choi matrices. So do you have any idea how the error rate would be likely to scale in that case? Because the diamond norm is really like the worst possible case.
That's a very good question. Yeah, so the error in that case will scale. For example, if your input to the simulation algorithm is close to the ground state, for example, then you would imagine that that the effective norm of each of these pieces will no longer, depending on the decomposition, depending on what the meaning of PJ is, you could have an effectively lower norm on each of these pieces. So the answer is yes, but it depends on the decomposition you're using.
So if we were using, I mean, if we cared about the difference between choice states for the channel, we would it would mean that the input to this would be a maximally entangled state.
Yes.
So 1/2 of a maximally entangled state.
Right. I have no idea really. This is I don't know. It's an important practical question, but to the best of my knowledge, this has not been this line of inquiry has not been addressed.
Okay.
Maybe I'm just not aware.
No. I mean, whatever it is, I'm sure it will be different from your method than from other methods anyway.
Yes.
It just seems much easier to calculate as well than the diamond norm.
Actually, well, it depends. Actually, the diamond norm works out to be very nice for this problem because the diamond norm is an operator norm. So we're using the fact that it's an operator norm to reduce the diamond norm to the 1 norm and makes things really nice.
Okay.
Mathematically.
Yeah, I do have another question. I'm not sure if anyone else has put up any questions yet, but I guess one of the other questions I had at the moment, both this method and the previous methods you've discussed, both the one from Charles et al. And Earl Campbell's method, each of them requires random choice.
Yes.
And so you're choosing to apply one channel or not with some probability.
Yes.
One might imagine a situation where instead what you did was you prepared an ancilla in a superposition and then conditionally applied one choice or the other, since the choices are themselves unitary. and then measured the ancilla and projected it back into the plus state. Do you have any idea how that might impact performance? Because it guarantees you always have a pure state, for example.
Right. Right. We haven't. I haven't thought about that. But what I imagine is that once you do although you prepare a pure state with this ancilla and you do the projection, once you do the measurement, it becomes effectively like a mixed state again. So in that case, I would imagine the performance would be the same.
Well, you would imagine that it doesn't become a mixed state because you do the projection and you're overwhelmingly likely to get a plus state.
Oh.
I think. I should say I haven't worked this out, but I think that that's the case. So it's kind of like the the bomb tester setup or something like that.
Well, okay. So if I put this on a more general framework, so maybe the question is, would some entanglement assisted scheme like boost the performance of this? And then if I put it from this perspective, then the answer is it shouldn't make it worse at the very least. So, but how much better? I don't know, but I imagine it would get better. But then the question is how well we can prepare this entanglement.
Sure, I didn't mean to put you in the hot seat. This is a super interesting talk,
Yes.
and I'm just I guess quite excited by these techniques. We care quite a lot about how to do Hamiltonian simulation and things like this. So it's really interesting to see new techniques. I'll let it switch back to Siwi because I'm sure she has some questions as well, or there may be some from the audience. Thanks, Yingkai.
Thanks, Joe.
Very interesting. There's still no questions from the audience, but I do have an implementation question, or at least a simulation question. You showed propane, I think carbon dioxide and is it ethane or ethanol? I forgot.
Ethane.
Ethane. Yeah. Is it for the runtime for these simulations? How long does it take you to run the algorithm for each of these molecules? Is it like of other days, hours, or?
All right.
And does it change with the molecules?
Right. So in our work, we did not actually simulate ethane or propane or carbon dioxide. In our numerical work, we ran a computer simulation to get an upper bound on the simulation error. So for that, these numerics came back fairly quickly. It took a couple of at most a couple of hours. But it was a fairly involved calculation, which heavily relied on the computer science expertise of David White on this paper.
Cool. I think Joe has another question. Please go ahead, Joe.
Yeah, I'm sorry to keep jumping in, Yingkai. I do have another what if question. And this is, so I guess I was just thinking, what are the potential ways that these things can be extended? It seems to me that at the moment, what you're choosing to do is in each of these schemes, you're kind of choosing to implement a single term in the Hamiltonian at any one point. Would that be accurate?
Yes, exactly. A single term, but of course the terms can be partitioned in your favorite way.
Exactly. So you might consider, for example, choosing a random commuting subset of terms or something like that. Have you thought anything in this direction, or if there's extensions that might work?
Yeah. So actually, there have been proposals. I'm aware of proposals in quantum simulation that try to make use of the commuting properties of subsets of Hamiltonian terms, but the difficulty with that is getting analytical upper bounds on the simulation error. So they can show numerically there is some improvement if you take into account the commutativity issues, but it's really hard to get these like rigorous bounds.
Okay. Yeah, sorry, that's it for me. I'll stop now. Thanks very much, Yingkai.
You're welcome.
Okay. There's still no questions from the Q&A from the audience. I guess if anybody has any questions, please do write them in now or raise your hand. Okay. I guess not. I guess, well, this probably brings us to the close of Tech Talks series, the third in the series. Thank you, Yingkai, again, for your wonderful talk.
Thank you, Steve.
Yes, okay. Thank you all for joining.